Okay, so these are the notes for section 1.5, Analyzing Graphs of Functions. So we're going to start by talking about the domain and range, which we talked about in section 4 as well. So the domain represents the x values, which is always left to right. The range is the y values, which is bottom to top. So we're going to look at this picture of this function and learn about the interval notation in writing domain and range and set notation for writing domain and range. So first, for interval notation, we're going to start with the domain. So you go to the farthest left of the graph and you're going to start with that number. Well, you'll notice the farthest left is at -6, but it has an open circle. An open circle means that it's not equal to -6. It gets really close to it, but it never equals -6. So we're going to start with a parenthesis, -6. Then I go to the farthest right of the graph. The farthest right that this graph goes is to 3. And it's a closed circle there, so I'm going to use a bracket, which indicates that it's equal to the value 3. Now we're going to look at the range of the function, which is bottom to top. So I go to the lowest y value, which is -7, and since it's a closed circle, I'm going to use a bracket. Then I go all the way to the top of the graph, which is a +7, and there's not an open circle there, so it means it does equal +7, so I need a closed bracket here. So parentheses are when something is not equal to. Brackets are when it is equal to. Other cases that we use parentheses are if you see infinities, if it continues going up forever or goes down forever, we use parentheses. That's also when we use an open circle, it will use parentheses. Closed circles are for brackets. So that's interval notation, which we use. The next is set notation, which you might see on a homework assignment or in the notes or in a book somewhere. So set notation looks like this, and as a mathematician we would read x such that -6 is less than x less than or equal to 3. What that means is that the x's for this function are between -6 and 3. It doesn't equal -6, but it does equal 3. Same thing for the y's. We would read it y such that -7 less than or equal to y is less than or equal to 7. So the y's are so that they are between -7 and +7, and they are equal to both of those values. Okay, the vertical line test we talked about in section 4 as well. A graph is a function as long as a vertical line only passes through the graph once. So if I look at an equation and I want to determine if it's a function or not, I'm going to draw several vertical lines across that function, or what I think is a function. If at any one of those lines it touches more than one time, it's not a function. But for this one, it only touches once on each line, so it is a function. Here's another example of an equation. If I draw several vertical lines, this one touches at more than one place. That means the x's repeat. So this is not a function. So you need to be able to tell, looking at the graph and looking at an equation, what types of equations will represent functions or not. Next, zeros, solutions, and roots. All three of those words are used interchangeably, and it's basically when the function equals 0, or where does it touch the x-axis, also known as the x-intercepts. So zeros because the y value is 0. Solutions, when you solve an equation, that's when y is equal to 0. Roots, I always think about the roots of a plant go into the ground or into the x-axis. Next, we're going to look at when a graph is increasing, decreasing, and or constant. Now, not all graphs are going to have all three things. Some may just be doing 1 or 2 or all 3. So I've got this function, and I want to look at the different places on this graph where it is increasing, decreasing, and or constant. So there's 2 places on this graph that it's increasing or going up. So that's highlighted in yellow now. So I'm going to write in interval notation the x values when this function is increasing. So this is from -9 to 3, or -3, and then it skips a space and it starts increasing again from 6 to positive infinity. Positive infinity because this graph is going to continue going to the right with that arrow. And I'll explain again the brackets and the parentheses after we finish. Next is decreasing, so that's when the graph is going down. So the purple section of the graph, it is decreasing. So that's from -3 to 2, this graph is decreasing. Okay, then the graph is constant when it's staying the same value. So it's going to be straight across left and right. So this graph is constant from 2 to 6. Okay, so if I look through my list of values, I should be able to start at the smallest x value and work my way through all of these numbers left to right, and it's going to represent all the x values across this function. So it starts at -9 and it equals -9 because there's a closed circle there. Then it goes to -3 and then jumps -3 to 2, 2 to 6, and then jumps back up 6 to infinity. So anything in the middle is going to use a parenthesis, and then the end numbers are either brackets or parentheses depending on if it's equal to or not equal to. When it's infinity, we use a parenthesis. Okay, next we're going to look at relative minimum and maximum. So a relative minimum is the lowest point on a graph. Now the reason we're using the word relative is because this graph continues up and down with those arrows. So technically it doesn't have a minimum or a maximum because it continues going down and it continues going up. Relative, we're going to ignore the arrow parts of the graph and look in between and find out the minimum and maximum value in between. So the minimum is the lowest point on an interval, and for this graph it's at -5, 0. We write the minimum and the maximum as an ordered pair. Then the maximum is the highest point on an interval, so for this one the maximum is at 1, 9. Okay, and in just a second I'm going to show you how to do this on your calculator when we get to the example. Okay, so example 1 says find the domain and range, and I've got two different pictures we're going to look at. First, we have a semicircle that goes -5 in all directions, left and right and up. So let's start with the domain. So domain is left to right. So imagine the farthest left that you can go and the farthest right that you can go. So this goes from -5 to +5. And I use brackets because it's equal to -5 and +5. Then for the range, we go bottom to top. So the very lowest part of the graph to the highest part of the graph. So the lowest this graph goes is 0, and the highest it goes up to is 5. So the domain is -5 to 5, the range is 0 to 5. Okay, now we're going to look at this picture, which is a rational function. And we're going to start with the domain, left to right. So I put the arrows left and right because this function does continue going left and right infinitely. But there's an imaginary line here at -2 that's called an asymptote where the graph never touches. It doesn't have a value at -2. So then the domain for this function is from -infinity to -2, and then -2 to infinity. Or you could say all reals except -2, but we're writing it in interval notation. So then when we look at the range, we look from the bottom to the top. Well, this has a horizontal asymptote at 1, and it continues up and down infinitely. So this is going to be from -infinity to 1 and 1 to infinity. Or you could say all reals except 1. Okay, number 2 wants us to find the indicated value of the function just looking at the graph. So remember, the number in parentheses is what we're inputting into the function, or the x value of the function. So if I go to -1 on the x-axis, then I go up or down to the blue line and find a point. I want to know what the y value is at that point. Well, at -1, the y value is +1. At f of 0, I go to 0 on the x-axis and up or down or wherever the line is or the curve is, and this is right here at the origin, so that's 0, 0. Then I go to +1 on the x-axis to find f of +1, and I go up or down to the blue line, and here's my point. So I count up, and f of 1 is going to be 3. Sometimes it's hard to tell on some of them that it's really close to. You're trying to find the point where it crosses at an intersection, a whole number if possible. Okay, number 3, we're going to determine if the graph is a function. So this first one, I have a picture here, and if I did the vertical line test, I would see that each vertical line that I drew across this graph would only touch the graph one time. So yes, this one does represent a function. Sometimes you're going to be given an equation, like y² equals 4 minus x. Well, I can use my calculator to look at the graph, but I have to get y by itself first. So to get y by itself, I have to take the square root of both sides. So when I take the square root, remember it's the plus or minus square root of 4 minus x. So I'm going to put this in my calculator, and I'm going to put it as two separate functions, this positive square root of 4 minus x and then negative square root of 4 minus x. Then I'm going to hit graph, and this is the picture that I get. So if I drew vertical line anywhere on this function, it's going to hit more than one time, so this is not a function. So you need to be able to tell looking at the graph or by plugging in the equation into the calculator and determining if it's a function or not. Okay, now number 4 wants us to approximate the zeros and find minimums or maximums. So we're going to look at the picture first and kind of approximate these three things, and then I'm going to show you how to look in your calculator and find them as well. So if I'm going to start with the 0 values, remember the zeros are where it touches the x-axis. Okay, so that's these 2 points right here, and we're just going to approximate these right now. So we're going to write these as an ordered pair, or you can just say x equals those two values. So I said x equals positive 2.5 and x equals negative 2.5, and this is just an approximation. Now, it's not always going to be the positive and the negative value of something. That's just a coincidence for this problem. Okay, so now we're going to look at the maximum value. Remember that this graph continues up infinitely. We're looking at the relative max or min. So that's this point up here, and I'm just going to approximate the ordered pair for that. And I'm going to say it's at about -1.5, 5.5. Same thing for the minimum. I want to find the lowest point on the graph, and that looks like it's right here. So again, just approximate -1.5 or +1.5, -5.5. Okay, so if you're just given a picture and you're not given the equation, you're just going to approximate these values. If you're given the equation, you can use your calculator to find all of these different things. And that's what I'm going to show you right now. So if I go to my calculator, and in y1, I type the function x³ minus 6x. So I'm going to graph it and see what it looks like first. Same as that picture that I had, maybe a little different because my window is a little different than that picture. So when you hit second trace, you're going to come up with this menu of options. So you can use 0, minimum, and maximum right now. That's what we're looking for. First, I'm going to do the minimum and show you the steps to find the minimum. To find the maximum and the 0, it's pretty much the same process. So you hit number 3 for minimum, and it's going to ask you 3 questions. It's going to say left bound, right bound, and guess. So you can sort of see my cursor over here. It is to the left of that minimum point, and I'm going to hit enter right there. And then after I do that, it's going to say right bound. So I take my cursor to the right of that minimum point, and I hit enter. And you're going to see these black triangles that pop up at the top of the screen. You're telling your calculator, hey, I think there's a minimum in between here, or hey, I think there's a maximum or a 0, whatever you're asking it to find. Then you're going to guess. So you're going to take your cursor to the lowest point for the minimum or the highest point, wherever you're trying to find. And you're going to hit enter for guess. Then it's going to come back and it's going to tell you what the ordered pair is. So the minimum for this function is actually 1.41, comma, negative 5.66. So my approximation earlier, I said 1.5, comma, negative 5.5. So I was close, but this is the exact minimum of this function. So you can do the same operations for minimum, maximum, and zero, and you'll all get the same thing. Okay, so now example 4, we're going to determine the intervals for which the graph is increasing, decreasing, and or constant again. So here's this function, kind of crazy. It's got lots of different bits and pieces going on. So first we're going to start with the increasing parts of the function. So increasing means it's going up. So from left to right, if it looks like it's going up. Okay, so this is the only part of the graph that's increasing. So I'm going to start with my interval notation, and I notice there's an arrow that goes left, so that tells me it keeps going to the left, negative infinity. Okay, and then the x value where it stops increasing is 0. So I'm going to write from negative infinity to 0, it's increasing. Okay, then I'm going to look at the decreasing part of the graph. So that's any place on the graph that it's going down. So this graph starts decreasing at 5, and then it's going to continue decreasing to positive infinity because it's going to keep going to the right. So from 5 to infinity, it's decreasing. And then this graph also has a constant spot, so that's in the middle here. So then from 0 to 5, it's constant. So remember, you should be able to go through all of your different intervals and connect the whole graph. From negative infinity to 0, it's increasing. From 0 to 5, it's constant. 5 to infinity, it's decreasing.